It's a great honor for us to invite to have I think all the Plurk founder here, and Amir is going to give us a presentation of some open source database that they used in Plurk. So let's welcome Amir.
Yes, thank you, Victor, and thanks for the invitation. So I'm going to speak about Redis, which is an open source database. So this presentation won't really be that much about Redis. I mean, Redis is the main theme, but I also hope to inspire and also talk about how we solve things at Plurk and what problems we have faced and how we have solved them. Because I think I don't really think Google will switch to Redis. I mean, you have your own databases, and so that's the reason why. I mean, it will be about Redis, but it will be more than that. So a bit about me. I'm a co-founder and a lead developer of Plurk. I have been there from the start, and I have helped Plurk scale to millions of users and billions items of data. So my general interest isn't really about databases. I can code in almost anything, and I'm coding on both front end, back end, and doing all kinds of shit. So but I do like scaling a lot, and I do read a lot about it, and I do care a lot about it. So my main philosophy is this, and it's a quote from Ghost in the Shell, which is an anime movie from Japan, and it is your effort to remain what you are is what limits you. So I think that developers should expand their horizons and do a lot of other things besides developing. And this is like design and copywriting and just being more creative. So let's begin on a journey on how Plurk ended up with Redis and what problems we really face. And in this journey, I will present what kind of problem really forced us into using Redis, and how picking a database isn't really the most crucial issue. I think solving problems and understanding problems and solving them creatively and simply is much more important than just picking a database, because a lot of times you can save a lot of effort and a lot of money by solving things differently. So this is the basic problem we have faced, and it is a lot of data growth. And this is based by the way that social networks work. So the more users you get, the more data you get. And actually this data grows exponentially. So this is a major issue. And this is why like Twitter and a lot of other startups have faced major issues with scaling up. And we have faced this as well. So there are different approaches to solving such a problem. And one of them is the easy solution. You throw a lot of money at the problem. You buy a lot of hardware, you hire a lot of people, and you build very complex solutions. And this solution didn't work that well for us because we don't have any venture capital. So we are using our own money, and we can't just say, okay, we are going to build 2 data centers to scale this up. So, but on most problems, you can do some compromises, and you can solve things partially. So, and this is like a better approach. You find a solution where the data grows linearly, and where you maybe don't solve every problem, but you solve them like good enough for most use cases. And how do you do this? Well, you do it by cheating. So it seems like you are solving the whole problem, but you aren't really. And most users don't really notice that you are cheating. So this is a great quote that really expresses this, and it is said that there is nothing so useless as doing efficiently that which should not be done at all. So I mean, if you are solving like exponential problems with exponential growth, then and you don't need to solve those problems, then your effort is wasted, and you have probably wasted a lot of money as well. So let's take an example with Plurk, and it's with our timelines. I mean, when we started out, we had like major issues scaling, and this is because our timelines just grew and grew in size, and users come, they start to follow users, they start to create content, and then over time it just gets bigger and bigger and bigger. And you can scale this, but it requires tons of hardware. So a creative solution to this is to make timelines a fixed size. So this basically means that they can't grow that much. I mean, and that means that your data also grows linearly. And what this also means is that there are some constraints, but and those constraints are of course significant, but for the users, they mostly care about recent data and about recent Plurks. So no user scrolls back like a month in time. So it doesn't really affect how they use the service. And we have solved this problem without using much hardware and without using much effort. Yeah. So this is like I think much more important than just picking a database. It's like thinking about the problem domain and solving things in a smart way. So you don't really have to put spend tons of time and money and stuff like that. After this, I think you also have to be reading and researching what others are doing, and the web is really great for that. I mean, you can follow some great blogs by like Google engineers and all other kinds of engineers that are blogging about their experiences. You can find articles like on how BigTable is designed, and you can get all kinds of ideas how databases work in general and how others have solved similar problems. And I think this is also a very important step. And it's also a step we have been on, like scaling Plurk up and picking the right database and coming into Redis. And then you can like research on what performs best. You can do benchmarking, profiling, and all kinds of tests like that to see which database really suits your needs. Yeah, so I want to tell you how we came to use Redis and what path we took. So we started out with MySQL, which many of you probably know. It's a relational database. It works pretty well, but the problem is when you get a lot of users, a lot of usage, then it does not scale that well, especially if you have like exponential data growth, then MySQL isn't that good a solution. So one of the optimizations we did was like, okay, we can't really let timelines grow on an infinite size, we have to limit it. And that's when we did that, and we implemented a distributed database called Light Cloud, which is open source. And yeah, so we implemented mostly for our timelines actually. And we based our database on something called Tokyo Tyrant, which is a Japanese database used by Mixi, which is a huge Japanese social network. And it's implemented in C, and it's basically a key value database with some pretty interesting features. And one of the most interesting features is Lua scripting. So you can basically script the database using Lua, and this enables all kinds of interesting opportunities. And one of those opportunities was to implement a fixed list. So that's what we did, and that helped us scale a lot, maybe to, I don't know, a few million users. But the problem is, and this is the problem by the most databases I have used, is that once you start to hit the disk and your data can't fit into the active memory, then the database performance drops down a lot. And this is what we experienced with MySQL, and this is also a thing we experience with Tokyo Tyrant and Light Cloud. So you really have to come up with a more creative approach. And this approach is to store everything in memory, and this is where Redis comes into play, because it is a mostly memory-only database. So what this means is that everything is stored in memory, and it's synced to the disk once in a while, so the data is still persistent. And this is the default behavior. Redis also supports like a normal usage where everything isn't stored in memory, but it's not really recommended. So what this offers is like amazing performance, and Redis performance is very similar to Memcached or Memcached. So it can do like 100,000 set operations per second, or 80,000 get operations per second. So this basically means that currently we can insert 100,000 Plurks per second, and that is many millions per minute and billions per hour. Yeah. So I mean, it offers really amazing performance. Yeah. So I like this quote, and I think this sums up the movement that is currently happening in the database space. And it is said that memory is the new disk and disk is the new tape. So this basically means that the memory will replace the hard disk. And you can see this movement a lot, like VaultDB, which is a relational database, a new relational database implemented by using the memory mostly. Yeah. So what does Redis offer other than a great performance and in-memory features? What it offers is, I think, one of the most interesting thing about it, and it's rich data types. So relational databases like MySQL operate on schemas, tables, columns, rows, indexes, etc. Column databases operate on similar things, while Redis really operates on key values, sets, lists, and hashes. And I think the thing that is most appealing about these data types is that they resemble the data types that we know in common programming languages, and this makes it a lot easier for us to think about the database. I mean, I have used like MySQL for about, I don't know, 5 to 10 years maybe, and I still don't really understand how to really optimize it, because it's so complex, and there are like many books written on just how to pick the right indexes, and I think this complexity is really slowing us down. And I think this is where Redis really is shining and will shine in the future, because it's just so much more natural to use. Of course, you can't use Redis for everything. I mean, if you are if you need like a relational database for your data, then it doesn't make sense to use Redis. And I think this quote sums up what the philosophy is by Redis, and it is that simplicity is the ultimate sophistication, and I think that Redis hits that simplicity, in that you can solve a lot of problems using just the normal data types found in programming languages. You don't really need all the features that like MySQL offers, because in most applications you don't really need them. Yeah. So now I will showcase some code I have written that uses Redis, and that really shows how powerful Redis is as a database, and how you can implement a lot of different things using just those simple primitives. So I have implemented something called Redis Trap, which is a wrapper for Redis, and it basically mimics the data types found in Python. So a programmer doesn't really know they are using Redis. Yeah. So the code looks like normal Python. It's a bit hard to see, I think, but basically, I mean, the problem is when you use like something like MySQL, you have to like wrap your head around it. Using Redis, you can just use your database as you use the normal Python data types, and I think this is really powerful. Yeah. So we have in the first example, it mimics a Python list. So you have something like append, you have length, and you can use the in operator. And all this uses Redis, but it's in the background. And all these operations are atomic. Then you have like hashes, which mimic Python dictionaries, and it's the same syntax and semantics actually as in Python. So a programmer doesn't really have to learn anything new. They can just use it, and they don't even know they are using Redis. And the last one is sets. So yeah, and the whole implementation of this is like under 100 lines of code. And I don't think, I mean, you can make other databases behave like this, but in Redis this is just natural, and the performance of this is pretty amazing. And as we will see in the last slide, Redis is currently adding a distributed layer, so you can like use this on many thousands of machines and have just a very powerful syntax. So, and this is again simplicity, and yeah, And this is done by, or said by Koichi Kawana, who designed Zen gardens. And he said that simplicity means the achievement of maximum effect with minimum means. And I think Redis does exactly this, and it enables you as a programmer to achieve this. So you can implement like stuff in a few lines of code, and it can do like all kinds of things. And in the next example, we will see how we can use Redis to implement a simple graph. And this graph can scale to a few million nodes currently. But using something like Redis Cluster in the future, it can scale to like many thousands of machines. And it's implemented in under 40 lines of Python code. And it's also open source, but I mean, anybody can implement it. So it's not really that big an issue. So if we see here, we have the basic primitives of graph. We have add edge, which can add edges between nodes. We have a has edge function, which can tell us if there is an edge between nodes. It has neighbors, and it can delete edges, and then we can set node values and edge values. So this is the basic primitives of graph. And like I said, this is super simple, and you can use it to implement all kinds of stuff with a graph database, like user recommendation. Graphs are pretty useful for that, or any kind of recommendation where you need to look at graph structures. So this is the basic implementation, and yeah, 40 lines of code. So you can see Redis enables us to implement something that may seem complex, but in reality we can just skim it down in maybe 30 minutes and be done with it. And like I said before, Redis in the future will be distributed. So you can like implement this and scale it on thousands of machines and have like a really, really powerful graph database that fits your needs, and you can extend it in any way you like. So I think you can get a lot of inspiration in a lot of different places, especially on like API design or database design, or I mean any kind of things. And this is from Charles Mingus, who is like a jazz god, and he said that making the simple complicated is commonplace. Making the complicated simple, awesomely simple, that's creativity. And I think what Redis enables is like creativity, because you don't have to like write 5,000 lines of code to implement a graph database. You can write it in 50 lines and just explore many different things. So next we will see how to implement a queue. So we use Redis for our queues as well, and we use them to process like many millions of background tasks. And this is again a great example of how you can just use the simple primitives to implement something that fits, that is implemented in 80 lines of code, and that can process a lot of things, and in the future it can scale like infinitely. So the basic queue is that you can put jobs in it, you can reserve jobs, and then you can delete jobs, and you can get some stats. So I mean that's very, very basic principles of a queue, and all those operations are atomic. Uh, and this is the basic implementation of it. So again, yeah, I mean, it's pretty simple. And I don't think, I mean, I have used a lot of databases before, and I have never used a database that enables such simplicity and such clearness as Redis does. So that's the reason, or one of the main reasons why I like it, because it's, it's just very, very nice to use. And when I use like MySQL, I have to wrap my head around it, and I have to fight it, and then it doesn't really scale, and then I have to like come up or find magic solutions where you can tweak a parameter and it suddenly scales and stuff like that. I don't really think that's the future of databases. And I mean, as Google, you probably have like maybe a similar system to Redis that's like hidden from away from you. But the most other programmers don't really have those kinds of solutions. So they have to like fight with the database system.
Last question here. Yeah. So here I'm seeing that you get a list and then a pen item, right?
Yeah.
What is the exact operation done underneath? Does it get the whole list from the database?
No, you don't. Everything is lazy. Yeah, it basically just fetches a connection which is cached, and then it just does a list append operation to Redis. So you don't really fetch the list. It's committed right away. I mean, I think actually that Redis is non-blocking, so maybe it's not committed right away, but I'm pretty sure that, or it is atomic. So when it's done, I think it's committed, but I'm actually unsure. I think also maybe that's you can configure that. So yeah. But I mean, Redis operates on memory, so it's like super fast. Yeah. Any more questions about this?
Actually, you probably been asked about this a lot. Since the database is in memory, how do you handle the data lost if the machine is down and it's not in the disk yet?
Yeah, so Redis has two things. First is replication. Another is like append log. So
where do you keep the append log?
I think it keeps it on the disk, but you can keep it in the memory. Yeah, but if you keep it in the memory, then it's not really. But I'm pretty sure it keeps it on the disk. So
wouldn't that be a bottleneck then?
Not really. I think the append log is updated in a non-blocking manner. But I think for most cases, if you just use replication, then it's not really an issue. And for us, I mean, if we lose like 5 seconds of data, it's not really that critical. I mean, it depends on how critical your data is. Yeah. So it's true that Redis offers less data security than something like MySQL. But I don't think, I don't think it's that bad. I mean, it's not an issue in like 99.99 of the cases. Yeah. So I will talk about the Redis cluster, which I think is like it will be a big thing because it will enable scaling of Redis across many thousands of machines. And it uses very similar scaling as BigTable and Cassandra, and it will just it will enable. Currently, the most used cases of Redis is like a highly optimized database where you just run it on a single computer, and that isn't really that smart. So the current solution you do is like you shard or partition manually, and that is an issue in a lot of cases. So you really want just a solution where the scaling and distribution is hidden away from you, and this is what a Redis cluster will offer. And there's like a link here, but currently it's like they don't really know 100% how they are going to implement it, but they are working on it, and you can follow that link, and it's like a presentation on how they want to implement it. But the basic ideas of the implementation is the same as we have seen in BigTable or we have seen in Cassandra. And I think also scaling or distributing Redis is much easier than, say, MySQL, because the data types are much simpler than, say, MySQL joins or relational database joins. So it just makes a lot of things a lot of more simpler, and I'm really looking forward to this feature. And I think Redis in the future can replace like normal databases like MySQL, Cassandra, or whatever, because the features, as I have shown, the features it offers is pretty much the core of what you need in most applications. So this is actually the end of my presentation here, and I will end it with this quote. And I don't really think that Redis is that perfect right now, but I think it's good enough, and I think it has a lot of great ideas, and I think we can learn a lot from it in terms of how to design our systems so they are pretty simple, and how to solve problems in a very creative way. And I think solving problems in a smart way and solving problems like with minimum means is a lot more important than just focusing on raw performance or what kind of database is the best. Yeah. So, any questions?
If you want to pop an item from the list and do some operation on that item and push it back, I know that push and pop are atomic, but will the composition of the whole session be also atomic?
Yeah, for some, I mean, Redis offers transactions, but you probably want like a manual lock on top, like a distributed lock on top of that, to, if you like, fetch a list and do some operations on it, you probably want to like lock it. And we actually use those kinds of locks in Plurk's code base, but they are implemented on top of memcache.
Oh, you mean Redis have a support a transaction, but you suggest us use a memcache to implement a lock?
Yeah, so it's like a distributed lock. I mean, the problem like with in Plurk is, of course, we have different servers, and we have to ensure that two servers aren't operating on the same list. Yeah, in some cases, I mean, for most usages, you don't really have that issue, but in some usages, you do have that issue, and I think it can be solved pretty easily using a distributed lock.
From the performance number you just gave, I noticed that write actually takes more time than get.
No, less. I don't know why. Yeah,
It takes 101.
I think maybe it's because it doesn't return anything, and I think, yeah, I don't really know why it's fast actually. That's interesting.
That you say set to get, right? And does it depend on whether the underlying data structure is a list or a set or?
Yeah, it does depend. So those performance numbers were for key values. They weren't for lists. But I think the performance is very similar for lists and sets as well. So it's probably one of the fastest databases, I think.
So in database usually needing to do a select try for the relational database. But how do I do a select and the operation in a list? Say I want to find certain elements, matching some kind of pattern.
You can't really do that. I mean, the thing you can do is like fetch the whole list and then filter it in Python. Yeah. But it does offer some things like regular expression matching on keys. So you can like get all the keys that are starting with A or something like that. Uh, the pattern matching of keys is done server side, but the custom filtering has to be done client side.
Say you store the recent product in the Redis. My question is, what database do you store all the data?
Oh, yeah. All the other data we store in MySQL. And yeah, we also still use the Light Cloud for some things like analytics. And we'll use like Redis for things that have to be performed really well.
For keys, if I want to do a membership test, saying okay, I have a key and I want to know whether it is inside the other one. What's the performance? If that how does that scale with the number of keys present in your database?
Yeah, on the Redis website, you can get like the complexity of most of the operations, and I think most of them are actually in constant time, especially on key values. I mean, the only like ON is like a regular matching because it has to look through all the keys. But like when you just access something, it should be constant time.
So you just mentioned Redis cloud. So right now Redis is running on single machine.
No, we have it on different machines. But I mean, like I said, with with this is that currently when you have to scale it out, you have to implement your own sharding, like you do in MySQL, and that is like a big issue because it's just, I mean, it can be optimized away, and yeah. So currently we are like manually sharding and partitioning, but with Redis Cluster it will be done automatically.
Which property do you shard? User ID or?
Yeah, user ID.
So if one user on server A is following a user on server B, then you need to do some kind of join operation.
Yeah, no, yeah, we don't really have to do that, but yeah, you could do that. I mean, yeah, like when you shard a MySQL or any other relational database, you mostly like you have to do joins in a client code. Yeah, so the same applies to Redis, but I think actually with Redis cluster, it will have like smart routing, so it will do the work for you. The joins or anything that affects like multiple servers. And yeah, that's, I think, is the greatest thing that will come.
You only store recent data in Redis, so user click a timeline to maybe 1 year ago, they you have to fall back to MySQL, right?
We actually don't really do that. I mean, the thing is, we store your plurks or a user's plurks in MySQL, so you can only always fetch your own plurks. The thing we don't store is like all your friends' plurks, and you can't actually scroll back that much back in time. I think you can scroll back like 500 plurks back, but most users, I don't think in the like 3 years time we have received very few complaints about that. So most users don't really know their timelines are limited. They are cheated.
You can find your own one, right?
Yeah, you can find your own and private, but it's like your all the others you can't really find.
Facebook and Twitter did the same thing.
Yeah.
You couldn't go back, like on Facebook, you couldn't go back after like two years or something.
So I cannot search for
Yeah, you can. You can. It's yeah. If you only search on your own, but you can also search on other users. It's just like your general timeline of all your friends' plugs. You can't really search that. But that is also the biggest issue in scaling like Plurk. It's that timeline of all the users, because it has most plugs. I mean, most users plug a few plugs a day or something like that. Yeah, they don't like plug thousands and thousands. So. More questions?
So, what's the namespace for the key? Just put anything, or you can have hierarchy, or
I'm actually unsure about it. I don't think you can put anything. I think it's very limited. Maybe only a ASCII. Yeah.
Even with restricted timeline, it still sounds like an exponential problem, because although the size is reduced in factor of 10 or something, but it's still an exponential problem. Because whenever a user joins, his friend will all add his latest work, and he will add his friends.
That's true, but I mean, you only allocate a certain size.
Oh, okay.
So it never grows like it has only a certain size. So each user you get, I mean, it grows in size for his own plugs, but yeah, and yeah, that's not yeah. So maybe the data patterns aren't really like linear, but they aren't like exponential, because they just grow. Yeah, they grow a bit, but yeah, it's not an issue because most users don't plurk that much that it's much worse like when you have all your friends. Yeah, when you have like a timeline with all your friends plugs, and it just keeps getting bigger and bigger.
so you said the limit of 500 words from my friend, right? Of mine. So
Yeah.
that means if I have like 1,000 friends working at the same day, I only get the most words.
Yeah, then you have a problem. But I mean, that problem can be easily solved by just like allocating more space for your user. I mean,
They don't see the plug, are not shown, so they don't know that
Yeah. Yeah, but I think most users can't really follow then they wouldn't really do much else other than plurking if they had 10,000 of plurk. Oh no.
I think there's a bit of a difference in terms of our approach because we sort of ascribe to Dunbar's number, which is in real life or in the offline world, you can really only have a maximum of about 150 relationships that you can keep, very close or intimate relationships that you really know about. Same thing with the timeline. Once you start to add hundreds and hundreds of people, your timeline is rendered ineffective. So it's the same. I mean, if you have Twitter and you're following thousands and thousands of people, you lose yourself in all that data. So there's a certain limit with kind of the approach that we've taken to our UI that you can only follow a couple hundred people before you say this is too much and it's information overload. So that approach tends to mimic real human interaction. And that's some of the psychology behind why we've done things certain ways.
About maybe not 100 friends, but like 100 friends each plug 10 times a day.
Yeah, but it's at a limit that it's still engaging and that we can keep users' attention spans on Plurks and actually interact rather than just with Twitter you have so much. Same with Facebook. There's really no limits. You continue to add friends and friends and friends, and then you're completely sucked into the system. So it's just I'm going to be spending 6-7 hours on Facebook. When is it enough? There's no limits or there's no constraints. It's more of a it's just not a very clean system, or it's not really meant for the user's benefit. I mean, I think we care a little bit more about our users, and so we've sort of developed things in a way that keeps that in mind.
I check out the website. You mentioned you have benchmark on that the set is quicker than the get operation, and
That's feature more. Yeah.
And your payload is 3 bytes. Is that too small for regular operation?
Yeah, I don't know. I mean, the benchmarks should probably be taken with a grain of salt, because
maybe that's why you get the set operation is quicker than the get operation, right?
Yeah.
I don't know, but their data is not like a real data.
No. I think it's just they have just done some, but I mean the performance is pretty good. So yeah, I generally don't really trust benchmarks that much because you can cheat on them.
I mean, because set operation is quicker than get operation is quite counterintuitive. So
yeah, it is.
I'm trying to figure out why that happened in benchmark.
But that is a good reason, I think, probably. Yeah. Thank you guys for listening on.